Hello class, and welcome to our video notes lesson on section 5.5, where in this lesson we're going to learn how to solve logarithmic equations. These are equations that contain logarithmic expressions in them. So there's two different types of a logarithmic equation that we're going to address in this video. One option is when every single term in your equation contains a log. So every item is a logarithm in the equation. And then the other option is if not every term has a logarithm. So some would have a log and then others would not. So what your first job is going to have to be is to decide which type of equation is it, and then based on that type you will follow whichever steps go with that type. So if it's option 1, where every term in the equation has a logarithm, these are the steps you're going to follow. In step 1, you're going to try to get it down to just one log on each side. So something that looks like this, a log on the left equaling one log on the right. So you don't want to have more than one log on each side. Also, this method only works if the base of each log is the same. So for all the ones that we're going to do in this video, they will be, and all the ones that we're going to ask you to do, they will be. But I just want to point that out. This method works when the log that we get on each side has the same base. Then what we're going to do next is set the inputs equal to each other. So that's kind of what this statement is referring to. This statement is also known as the one-to-one property. So what this property is saying, and this is true for functions that are said to be one-to-one, and logarithmic functions are functions that are said to be one-to-one. And we're going to learn more about that in our next unit. But for right now, all you have to know is that they follow this property, which if I were to take just this equation up here, so y equals the log base b of x, we consider the thing inside the log to be the input, and we consider what the log equals to be the output. So what the one-to-one property says is that for each different input, you'll have a different output, and vice versa. For each different output, that would have come from a unique input. So what that means is if you have a situation like this where it seems like you have two different outputs, right? Because this would be an output equaling, actually no, this is saying they're the same output, right? Because they're equal. But the inputs are different. X is different and Y is different, but this equation is saying that the outputs are the same. So if a function's one-to-one, the only way the outputs could be the same is if these inputs were the same. So what we can do is say, oh, okay, let me just look at the x and the y and set those equal to each other. So that's what this step is referring to. Then you just solve basically a semester 1 equation at that point. It'll either be linear or quadratic. You solve it. Then you're going to check your answer. And it's important to do this with logarithms because the logarithms have a restriction on what can go inside them. So the input of a log, the thing that we plug into the log, can never be 0 or less than 0. So it can never be less than or equal to 0. So sometimes when we get our solution and then we plug it back in for x, the value that we get inside ends up being 0 or negative, and those values, I guess, are what we would call extraneous solutions. So maybe I should say here, check for extraneous solutions. Solutions that worked out for when I set the inputs equal to each other, but they don't work when you plug them back into the original equation that had the log, just based on the fact that you can't have a negative inside of a log. And just a really quick explanation why we can't plug a negative inside a log is because of this. So if you think back to this generic logarithmic expression, the y is the exponent, right? Whatever the log equals is the exponent. This subscript here is the base. And then the input, the thing that we plug into the log, is actually the answer to the exponential equation. So this could be rewritten to look like this. You have your base b, you're raising it to your power of y, and all of it is equaling x. So because the inside of the log is an answer to an exponential equation, it can never be negative because I never get a negative number when I raise a base to a power. Like even if I were to raise the base to a negative power, that would just take the reciprocal, right? And remember, our bases are always positive. And so when you raise a positive number to a negative power, it just takes the reciprocal. So there is never a time when the answer is going to be negative, and since that's the part that's going inside a log, there's never a time when the input of a log would be negative. It just doesn't make sense, so it doesn't exist. So we just have to check and make sure that our solutions don't create that type of situation. Okay, so then if you have option 2, so option 2 is when not every term has a logarithm. Instead of getting a log on each side, we're just going to isolate the log. So if there's multiple logs, we're going to use the properties to condense them and get them all on one side, and then get everything that doesn't have a log on the other side. And then once we have an expression that looks kind of like this, so this is a log on one side and then something on the other, we're then going to rewrite it into exponential form like this, and then be able to solve for whatever we're looking for. So then we'll solve, and then of course we'll check our answer to make sure that there are no extraneous solutions. So let's go ahead and try that with number 1. So I want you to look at number 1 and kind of check to yourself, like which option is it? Is it option 1 or option 2? So notice that in example 1, every term has a logarithm. So this is an option 1 equation. And also, step 1 has already been done. There's already one log on each side. They both have the same base. So we're going to go ahead and just use the one-to-one property here. This is a property that logarithms have that says, hey, if these outputs are equal to each other, the only way that's possible is if their inputs are equal. So we just take the inputs and set them equal to each other. So that was step 2 right there, because step 1 was kind of already done. And then now this is just a linear equation. So I just solve it using first semester strategies. So just get the numbers together on one side, the variables on the other side, basically just trying to isolate the variable and then isolate the variable. So I get x is 6. So this is the solution I get to the equation in number 1. So I just want to check and make sure that if I plug 6 into either of these logarithmic expressions that the inside stays positive. So here, if I plugged it in, I'd have 12 plus 1, so that's positive. And then here, if I plugged it in, I'd have 18 minus 5, which is also positive. So this is, in fact, our solution for number 1. Moving over to number 2, what I want you to notice is that these two terms each have a log, but then this one doesn't. The 3 on the other side has no log. So this is going to be an option 2 scenario where not every term has a log. So what we're going to try to do is isolate the log. So right now there's 2 of them, but we're going to try to combine them together using the properties of logs to condense. So since these 2 logs are being added, I'm going to use the product property of logs. And just as a side note, that's the property that says if you are adding 2 different logs with the same base, that is the same thing as having a single log with the same base and multiplying the inputs. It's called the product property for logs. So in this case, our inputs are 6 and x. So this is equal to the log base 2 of 6x. And then that is equal to 3 because I didn't really have to do anything on the right side. So now I have a single log equaling 3. So what I can do at this point is rewrite in exponential form. So I want you to make a big deal about this on your outline because this is the part where students often forget what to do next. This is step 2 of option 2. You're going to write in exponential form. That's when you remember this property up here, that the subscript becomes the base, the thing inside the log is the answer to the exponential question, and the log equals the exponent. So using that down here, 2 would be my base, 6x is the answer, so to speak, and 3 is the exponent. So we're going to rewrite this and we're going to say 2 to the power of 3 is equal to 6x. Base, exponent, answer. And then solve. So that means 8 is equal to 6x, and then I just have to divide by 6. So I get 8 over 6, and then if you reduce that, you get 4/3. And I can tell that the only log that had an x in it was this one, and if this was equal to 4/3, that would be a positive, so then this answer is fine as is. So on to example 3. This again is like an option 1 because each of the terms has a logarithm. So what we're going to do is take the inputs and set them equal to each other. So we're going to skip to step 2 again because step 1 was already done. So we're basically using the 1-to-1 property again, which tells us that if these outputs are equal to each other, right, which is what the equation's saying, then the inputs must be equal. So we'll set x plus 5 equal to 3x plus 31. And then I will just solve for x. So I'm going to combine the variables together on one side and then isolate it by moving the numbers to the other side and then getting x alone by dividing. So for number 3, I get x equals negative 13 is my solution. So I just need to check and make sure that I'm allowed to plug that into these 2 different logs. So I notice on this side, if I plug in a negative 13, that would get me a negative value. So I actually am not allowed to let x equal this because that would create a negative in here. And then here, if I plugged in negative 13, same thing would happen. I would end up with a negative number inside the log, which I'm not allowed to have. So actually, this one in number 3, it has no solution. You could say it has an extraneous solution of negative 13. So like that's what we get if we solve this linear equation right here. Because linear equations have no restriction, like those values can be negative or positive. So that's why this linear equation was allowed to have a solution that's negative. But because the original equation was logarithmic and there is a restriction on what we're allowed to plug into a log, that solution doesn't apply to the log equation. So the log equation has no solution. So over here in example 4, we're working with the natural log, right? So the natural log of x, you would read it this way, natural log of x. That's how you read that. And what it stands for is a log of base e, where e is that number about 2.71-ish. So it may help you to kind of rewrite each of these to remember that they are just logs like any other log. It's just sort of an abbreviation because this log is used so much. It's the natural log. So it's just sort of an abbreviation of a log base e. But it might help us see, okay, every single term in this equation has a log. So this is an option 1 style problem. And so I'm going to have to try to get 1 log on each side. So this side's already done. This one over here has only 1 log. This side has 2, and I'm going to need to try to combine them. So because I'm subtracting the logs, we're going to use the quotient property of logs. Quick recap of what that is. That basically says if you have a log base b of one thing inside minus another log with the same base of something different inside, that's the same thing as having a single log with that same base and then dividing the things that are inside. So we're going to use this property to combine these 2 logs into 1. So that's going to create log base e of 4 divided by x. So now I have 1 log on each side, and these logs have the same base, right? So I'm going to go ahead and use what's called the 1-to-1 property. I want to keep repeating that so that you will remember that that's what's allowing us to do this. It only works for functions that are considered to be 1-to-1. And again, that means if you have 2 outputs that are equal to each other, the only way that's possible is if the inputs were equal. So we just take the inputs and set them equal to each other and then solve. So what I'll do is I'll multiply x to both sides to get 4 equals 36 times x, and then divide both sides by 36. So I end up getting x is equal to 1 over 9. So if I look back at my original equation, this solution's fine because it's positive, and the only logarithm that had an x in it was this one, and it was by itself. So if I plug in 1 over 9, that totally works. So this is our solution for number 4. Now in number 5, this would be an option 2 type of logarithm because there's 3 terms, but this one, the last one on the right side, doesn't have a logarithm. So not every term had a logarithm. So this is an option 2. So we're going to try to isolate the log. So we're going to try to combine these logs together here. We're going to use the product property because the logs are adding. So I can rewrite that as 1 log with the same base of the product of x plus 2 and x minus 4. So on the left side, I have 1 log. On the right side, I have no log. And again, I want you to make a big deal about this part on your paper. At this point, when you have a log on one side and a non-log on the other, so I'm going to put log, non-log, at this juncture is when you rewrite the equation in exponential form. So that's important to really stress that to yourself so you don't forget. So I remember that 4 is the base. Whatever the log equals is the exponent. And then the thing inside the log is the answer. So rewriting in exponential form, I would have a base of 4, an exponent of 2, and an answer of x plus 2 times x minus 4. So I get 16 is equal to, and I'm going to go ahead and FOIL this side out. So that'd be x squared minus 4x plus 2x minus 8, which is this. And so I'm going to either have to factor or use the quadratic formula because an x squared emerged in my equation, right? So I got to get 0 on one side. So I'm going to move the 16 over. So here I'm going to see if it factors, because if so, that's easier. So are there two numbers that multiply to negative 24 and then add to negative 2? And the answer is yes. That'd be negative 6 and positive 4. So if I split up that middle term and factored, then I get here 0 is equal to x plus 4 times x minus 6. So my two solutions at first, here, let's go up here. I have one solution where x plus 4 is 0, and then that would give me an answer of negative 4. And then I have another solution where x minus 6 equals 0, and then that would give me x equals 6. But let's check and see if I'm allowed to plug these values in. So let's see here. This was our original equation. So for the negative 4 option, if I plug that in here, I'd have negative 4 plus 2, which is negative. So I can't plug in negative 4. So this one would be considered an extraneous solution. Something that we got as a solution to the quadratic equation, right? This equation was quadratic. So that would be a solution to the quadratic equation, but not a solution to this logarithmic equation when the logs are still there. So it's an extraneous solution. So this is our only actual solution. So if we ask for the solution, we would only want you to put x equals 6. We would not want you to put both. Sometimes, though, we may ask you for the extraneous solution, and we're talking about the solution that you can get when you solve the equation, but that doesn't work when you plug it back in to the original equation. Okay? So this equation has only one actual solution, which is x equals 6. Why don't you guys go ahead and try number 6? Okay, so looking at the work here, first what you're going to want to do is move this log to the other side by subtracting it over. Move the 2 to the opposite side by also subtracting it over. So that's how I ended up with minus 2 log 5 of 10 and then negative 2 on the right. Then I can bring up this 2 that was being multiplied to the log. I can use the power property of logs to make that the exponent of 10 inside the log, which turns it into 100, because 10 squared is 100. Then, because the logs are subtracting, I can combine them into a single log where I'm dividing the x and the 100. And then right here is the part that you have to really remember to rewrite in exponential form. So the 5 was our base, that's right here. Whatever the log equals is the exponent, so that goes here. And then what's inside the log is the answer to the exponential equation. And then 5 to the power of negative 2 is 1 over 25. And then I can just multiply both sides by 100 to get our answer of 4. So for the last part of these video notes, we're going to just look at how we could find x and y intercepts for logarithmic functions. So in our next unit, which is unit 6, which is all on graphing, we're going to be looking at the graphs of functions that look like this. And it will be helpful to be able to find the x and the y intercepts. But that uses a skill from this video, right, solving logarithmic equations, which is why we're teaching this to you now so that you can use it eventually in Unit 6. So finding x and y-intercepts is the same for every function. For an x-intercept, which remember, if you're looking for an x-intercept, something on the x-axis, the ordered pair for that would have an x value in the x-coordinate spot, and then it would just have a 0 for y. The only way you can be on the x-axis is if y is 0. So knowing that, we can plug in 0 for y and see what we get for x, and then we know that that would tell me where the graph will cross the x-axis. Similarly, when we're trying to find a y-intercept, something that's on the y-axis, we know that the only way you could get a point on the y-axis is if your x-coordinate is 0, and then your y-coordinate is some y value, which would tell you how high or low your point is. So knowing that, we can plug in 0 for x in the equation and then just evaluate for y, and that'll tell us like where the graph hits the y-axis. So in this one here, we'll go ahead and start finding an x-intercept. So we're going to plug in 0 for y. So 0 is equal to the negative log base 3 of x plus 5 plus 2. So this would be like an option 2 style because not every term has a log, right? The 0 doesn't and the 2 doesn't. So what I'm going to do is subtract the 2 over to isolate the log. We want to get the log by itself. Then we're going to go ahead and divide both sides by the negative 1 because we want the log all the way isolated. And then this is the part where we rewrite into exponential form. So we have to recognize that our base is 3, our exponent is 2, and the x plus 5 on the inside of the log is the answer when writing in exponential form. So this expression is equivalent to saying 3 squared is equal to x plus 5, or 9 is equal to x plus 5. And then from there we just isolate x, subtract the 5 from both sides, and we find that x equals 4. So what that tells me is that this graph will cross the x-axis where x equals 4. Okay, and then for the y-intercept, we would do a similar process, except we would be plugging in 0 for x. So I am going to do that over here. So now I'm plugging 0 inside the log. So I have y is equal to the negative log base 3 of 0 plus 5 plus 2, which is negative log base 3 of 5 plus 2. So you can write this in a number of ways, but this here would be considered the exact form, right? This is no decimals, no decimal approximation. This is just the exact form. And you can write the exact form in a couple of ways. You could write it like this, 2 minus the log base 3 of 5. So you could just reorder that and make sure you keep the log negative. Or you can think of it as the log base 3 of 1/5 plus 2, because if you think of the negative in front as a negative 1, you can think of that as the exponent inside, and something to the negative 1 power would just flip it over. So either this or this is fine. Each one of these are all referring to the same value. Then if we wanted to get the decimal approximation, because since it's not a whole number, if we wanted to kind of understand relatively like what value that would be, we could use the change of base formula to evaluate this expression in a calculator. So just a really quick recap. When you have a log base b of a and you want to change it into a base 10, that would be a log base 10 of a divided by a log base 10 of b. So this expression here would be 2 minus log of 5 over log of 3. I would plug this into a calculator, and that would get me approximately 0.535. That's approximately what that would equal. So that means that on the graph of this function, it would cross the y-axis at the point 0, 0.535. So it crosses the y-axis roughly around 1/2. And I forgot to say over here, for the x-intercept, we should write it as 4, 0. We should always write our intercepts as ordered pairs. Okay, so why don't you guys try number 8, which by the way on your outline is a typo. It says 9, but it should say number 8. And that reminds me as well, if you go back here on your outline it says exponential function, but it should say logarithmic. So if you could change that as well, those 2 typos. And then go ahead and find the x and y intercepts for example 8. Okay, so let's first start by taking a look at our x-intercept. That's where we plug in 0 for y, right? F of x is another name for y. We can replace it with 0. And then this again is an option 2 equation, so we want to try to isolate the log. So we start by adding the 6 over and then dividing by 2 to get here. Once we've isolated the log, we rewrite in exponential form. So our base was 1/2. Our exponent was 3, and then the thing inside the log is the answer to the exponential form. 1/2 to the 3rd power is basically 1/2 times 1/2 times 1/2, which is basically 1/8. And then I just subtract 1 and get -7/8. That would be my x-intercept. Now you may be wondering, how are we allowed to have a negative solution? Because if you go back to the original log, there's an x plus 1 inside the log. So if I were to plug -7/8 in for x, I would have -7/8 plus 1, which is equal to +1/8. So this negative value is okay because I was adding 1 to it inside the log. So the overall value inside the log was still positive. Okay, and then for the y-intercept, this is where you plug in 0 for x in your equation. So you get 2 times log base 1/2 of 1 minus 6. But we can evaluate this log because we know that if you take 1/2 and raise it to the power of 0, that would equal 1, right? The thing inside the log is the answer. So 1/2 to the power of 0 is 1. Therefore, this whole entire log is just equal to that exponent of 0. So the whole thing is 0. So then you just have 2 times 0, which is 0, and then minus 6 is -6. So that was our y-intercept for the last one. That concludes this video, and I will see you in class to practice these together. Bye.